So my name is Sriram Rajamani. I lead Microsoft Research in India. And thank you for inviting me. I'm very happy to be here. So my goal in this seminar is to demystify, what you've been hearing about. What is this ChatGPT? What's actually going on? What are all these AI models? What do they do? And you hear a lot of, it's very hard to actually open a newspaper and not find an article about it today. Any newspaper will have an article about it every day, right? And there's a lot of hype about this as well, right? And there are questions like, will these take away our jobs? Will these take over our lives? And people have various opinions, right? My goal here is not to give an answer to this question, but to give you enough background so that you can make up the answers yourself. That's my goal. My goal is to give you enough background so that you can reason about what this AI is, what it can do, what it cannot do, how to use it responsibly, what are its capabilities, right? And what are ethical issues? And I want to give you the tools and the background to answer those questions yourself, right? That's my goal. And in order to do that, right, I will have to start with a narrative on what intelligence is, what is AI, and then talk about maybe some of the mathematical background behind what these models actually do. I mean, I was not entirely sure, how much math I could use, but I heard that you all just went to a math class, you have just done some calculus, maybe some stats, and so on. So maybe I'll also do some whiteboarding. I'll do a little bit of math as well, so that you sort of understand what's behind this, right? And we'll keep this interactive. You can interrupt me and ask questions. But I do need to finish, so if you ask too many questions, I might pause you a little bit, right? We'll just go that back and forth, but just interrupt me. Okay, are we good? I would really appreciate silence, right? I came all the way from Bangalore and I want to talk to you and I want you to talk to me, okay? So, good. Are we good with this? Okay, so if you want to talk to someone, talk to me. Don't talk to your neighbor right now, okay? So, so let's see how these slides advance. Okay, so a little bit background about myself. I'm from Tamil Nadu. I did my bachelor's at Gindi Engineering College in Chennai. Then I went to the US. I lived in the US for about 15 years. I did my master's at the University of Virginia at Charlottesville. And then I did my PhD at the University of California at Berkeley. All my education is in computer science. And before doing a PhD, I worked for about 5 years as a programmer. So I did some programming in the industry. And after my PhD, I've been with Microsoft Research. Microsoft Research is an industrial computer science research organization. I first joined Microsoft Research in Redmond in the US. And then Microsoft Research India was started in 2005, and I came back to India in 2005. And since then, I've been here in India. I've been doing computer science research in India. And as of 2017, I've been heading our lab. So this is a little bit of my background, right? So, typically, people like me will have a CV, which actually not only lists this, but it will list awards that I have won, titles that are given me, and they will say all those things, right? But typically what a CV does not list is actually, failures that people like me have had. So Ambika asked me to also list the things that I don't list in my CV, right? So I thought I should tell you about that. As a young student, right, I wanted to get into IIT, but I did not get a good rank. So I was from Tamil Nadu, so I did get naval architecture at IIT Kharagpur, which, by the way, is a good branch, but I was not interested in it. I wanted to do computer science. So I went to Gindi Engineering College. In my mind, right, I thought, IIT was the biggest thing I wanted to do, and I didn't get that. But actually, it turned out that Gindi is a great place. I learned many things. I made many great friends. And I had a really enjoyable undergrad program. And then after I graduated from Gindi, right, again, I wanted to go to like a place like MIT or Stanford or Berkeley, but my GRE scores were not very good. So the best university I could get into was the University of Virginia, Charlottesville, which is not a very highly ranked university. But again, actually, it was an eye-opener for me. And in retrospect, I was really glad that I went to a place like Charlottesville, because academically it was easier for me to break into the US, right? Go to a new place. And I would think that actually, if I had gotten into a place like Berkeley directly, it would have actually been more challenging for me to get in. And then, the difficulties continued. After my master's, I was not quite sure what I wanted to do. I looked for a job. It was very difficult for me to find a job. There are many job interviews. Many people rejected me. And then I found one job in Washington, D.C. I worked there for a while. And the job was actually not very demanding. It was not even interesting. But it gave me a lot of time to prepare for my GRE again. And then I took my GRE again. I worked in the industry for a few years. And the second time I applied, I did get into very good schools. Then I got into Berkeley for a PhD. And the missed opportunities continue. I did my PhD in an area called formal verification. It's a very interesting area. But let me tell you, actually, when I was at Berkeley, it was in 94 or 95, I think. At that time, the internet was there, but search engines were not there. So I attended a talk by this professor at UC Berkeley called, his name is Eric Brewer. He was actually talking about the fact that we should actually build a search engine. He said actually we should be, see at that time, if you, the only way to go look at internet pages, but you have to also know the address of the page. You have to know the HTTP address. You could type Microsoft.com and you could go to Microsoft. But you couldn't actually search because search engines didn't exist. So he was giving a talk, saying actually, you know what we should do? We should actually crawl the entire web. We should index it, and then we should actually search for things. I thought that was such a bad idea, right? Why would somebody do that? Because I was thinking, why would I even go to a website if I didn't trust it? And if I knew the address, I know where to go to. And that gave me like, revelation. Now that I think about it, right? The future is so hard to predict, right? The so-called, pundits, when they tell you this is going to happen or that is going to happen, more often than not, they are just wrong, right? So I remember sitting in that audience thinking, why would you even need a search engine? Now we can't imagine life without a search engine, right? Our failures continue. Since then, I've become a professional researcher, but I routinely have my technical papers getting rejected. So what happens actually is that you write technical papers in conferences, and then they are peer reviewed. Many of my papers have been rejected, right? And of course, I don't list the rejected papers in my CV. I list only the accepted papers in my CV. And of course, I've gotten many papers accepted as well. And several research projects I've worked on have also failed. But some have succeeded in a big way, and those are the ones that I'm known for, right? So I hope it sort of gives you that, and I'm not alone, right? Everybody who came, like all these 9 people who came and talked to you probably have things like this as well, right? So please don't get intimidated, that people succeed. Everyone has ups and downs in their life, right? So I hope, Sambika, I hope I served, the
It's very important for them to know that it's not all about succeeding like a Superman.
Yeah. Yeah, so everything, life has its ups and downs, more downs than ups actually in many cases, and we just go through them, and I think the ups actually keep you up. That's what they do, right? So now let's get to the talk of demystifying generative AI. I'm probably, I feel a little bit like the previous generation in this audience. How many of you even have seen this movie? How many of you know what this movie is here? What movie is that?
It's from Terminator, where the robots have made AI. And the last scene, the demon knowledge said that there is money behind everything. Those are things that
Yeah, that's very good. And then this one, the one on the slide on the left, right? The picture on the left is T2. That's the Schwarzenegger movie. I think that's the Terminator 2 movie is, I think, the best in the series, right? If you have not seen it, right, you should watch it. It's like it's awe-inspiring, and it's incredibly well done as well. I remember, I watched this movie as a young boy, and I used to wonder, is this even possible, right? Do these Terminators, can somebody ever build this AI, right? And will the machines take over the world and enslave all human beings, right? That was the premise of this movie, and will this even happen, right? And that's a very important question today. It's more feasible now than it was before, right? So one of the goals of my talk is to give you the background so that you can actually answer that question yourself. Can these machines be built today, right? I'll give you the background to answer that question yourself, right? Now, before I go there, can these machines be built? Let's actually get back to the basics on what is a computer, right? Can computers do these things? Can computers become these humanoid machines? But what is a computer? Maybe I can ask somebody here for a definition of a computer. What in your mind is a computer? What is a computer and what can it do? Maybe show of hands. Yeah, you.
compute values.
It can compute values. Okay, maybe the boy there. Yeah.
It just does whatever you instruct it.
It just does whatever you instruct it to do. This girl here. Yeah.
It's a device that sort of gives you an output based on the series of inputs you give it.
Okay. Maybe
and
we can
used to
take-
solve
To
problems.
solve problems, we can, one last one, and then I'll take you later. Yeah. Thank you.
So
Yeah.
computer is a machine that computes tasks, as she said. So basically we provide inputs and it provides outputs, but it does not have its own brain, so it needs a modem to work with.
Okay, so I think, we'll stop now. And, this is actually something I got from Wikipedia. I think the synthesis of all these answers is that it's a device that can be instructed to carry out a sequence of instructions. Right? You can actually tell a computer, do this, followed by this, followed by this, and the computer can execute it. Right? And, I think she was saying that it doesn't have a brain on its own. All it can do is actually execute a set of instructions that somebody has programmed. That is what a computer can do. Right? So that's a far cry between something that executes a bunch of instructions and, I guess, Arnold Schwarzenegger, right? There's a big difference between those two. So what the hell is going on here? Right? So that's why actually, that's what we're going to go. How can a computer that actually just merely follows instructions, become, Terminator? Why is that possible? Right? Why might that even happen? Right? That's actually what we will get into. But before we get into that, right? Maybe a question to ask ourselves is actually, what all can computers do and what all can they not do? Right? We actually talked about what they can do. I mean, they can follow a set of instructions. Can you have a sense of what a computer cannot do? Maybe I'll get 3 answers. Yeah, go with that girl here. Yeah.
So first of all, like it's okay, I'm a joke sort of answer like a serious answer.
Okay.
Serious answer of computer, it cannot start its own code unless it all things in program. Like
Okay, I'm sorry, I can't hear you. Yeah.
So a computer, like I have 2 answers. One is a serious and one is like a joke sort. So the serious answer is that a computer, it cannot do anything on its own unless it has been programmed and for a specific time. Like even if it's being updated, auto-update, like Microsoft, I think some of them does, it has been programmed for a specific time and for like vendor computer modules and
Okay,
something.
it can do only things that a program that a program asks it to do. It cannot do anything on its own.
Yeah, it cannot do
Okay?
anything.
And what is the joke?
The joke is that it cannot swim, fly, eat, or basically sleep on its own. So.
Okay, that's interesting. By the way, I can actually put my computer to sleep, by the way, right? So I was not talking about that. Let's actually even, somebody, was it you who said actually it could solve mathematical problems? Somebody said here actually it can compute values. Can you actually think about a mathematical problem that I can state that a computer cannot solve? So let's not worry about sleeping and eating and so on, right? Oh, yeah, of course, those are important. I mean, those are important things. But can I actually write down? Yeah, how about that? Yeah.
There's a huge amount of data.
Yeah.
There's a huge amount of data to be analyzed, or a mathematical problem that includes of infinite recursion, then that kind of a problem cannot be solved by conventional computers.
That's interesting. This boy here, yeah.
Many problems that we've ourselves said that are unsolvable, like the Riemann hypothesis or the Collatz conjecture.
Like the Riemann hypothesis,
Yeah, or
right?
the Collatz
Like there are
conjecture,
many
things like
problems
that.
mathematically nobody knows how to solve them. How can a computer solve them, right? So those are examples. Last one, let's give this girl. Yeah.
It cannot tell the value of pi.
It cannot tell the value of pi. Okay, that's interesting. Okay, so actually these are not very interesting answers, right? Let me tell you something, right? Of course, actually, I mean, pi. I'm sure we can have a computer keep printing the value of pi forever. That's possible. But let me show you this problem. This is a mathematical problem, right? Suppose I give you a program. Now, I think this girl was saying actually that unless I give a program, the computer can't run it, right? Let's take a program like Candy Crush Saga. How many of you have played Candy Crush Saga? I'm sure all of you played Candy Crush Saga, right? Right? Suppose there is a version of Candy Crush Saga that will hang. So sometimes Candy Crush Saga hangs as well, right? Can I have a computer that takes the Candy Crush Saga program as an input and determine ahead of time, when I run this program, will this program hang or not?
It should be able to.
Why?
Well, it can't be 100% accurate, but it can check how much RAM it is currently using and
how much RAM it currently is using, and along with the usual RAM capacity that Candy Crush Saga uses, and determine if it has a higher likelihood of hanging or not.
Yeah, so maybe it can do likelihood, okay? But it turns out that you can actually prove mathematically that there is no computer that can take a program and determine definitively whether it will hang or not. It is not possible. That is actually mathematically proved, right? In fact, actually, I mean, it's not something that I'm saying. This problem is many hundreds of years old. It first appeared in this paper by Alan Turing, right? And in fact, actually, this has come in many, many other guises as well. There is actually a church hypothesis. There are many, many things. But this is called the halting problem, right? If I cannot build a program Q that can take another program P as an input, P and some input X, and say, does this program P on input X, will it halt or will it keep running forever? This problem cannot be solved by any computer. It's called a halting problem. It cannot be solved. And in fact, actually, one of the things you can, and by the way, the proof of this is not very hard. I'm not going to give the proof. Maybe I'll give this as an exercise. You can do that by proof by contradiction. What you can do is that you have to assume that such a program exists, such a Q exists, right? And then what you can do is actually you can feed some variant of Q to itself, and you can arrive at a contradiction. So how many of you know how to do proof by contradiction? How many of you have been taught how to do proof by contradiction, right? So here's a homework exercise for you. Prove that this theorem is correct by contradiction. Right? I'm not going to go through that, but you can actually prove that such a program Q that actually can analyze another program P and this determines whether it halts or not does not exist. So this is an example of a mathematical problem that cannot be solved by a computer, right? But then actually, maybe this is not the most interesting one. Now this is along the lines of whether a computer can eat or not. Can I now ask, do these flowers look beautiful? Are they smell sweet? Can a computer answer that question? Maybe it can, but you might not be satisfied with it because the answer to this question is somewhat subjective. Right? One person, you might think this flower is beautiful, and you might think it's not beautiful. So what is a computer supposed to do when it is given this question? Not entirely clear. This is a nice poem. I think it's a nice poem. Can a computer determine whether this poem is nice or not? That's also not very clear because it's very subjective, right? This one is a haiku. I actually, for the heck of me, don't know how to appreciate haikus. Does anyone know how to appreciate haikus here? Okay, somewhat. But again, right? Is this a good haiku or not? I'm not entirely sure. Because that's a very subjective question, right? So then you might think, okay, so there are some mathematical problems that a computer cannot solve. Definitely, whether a computer cannot determine whether a program is going to halt or not. That's a mathematical problem. Maybe a computer has difficulty answering subjective questions because they're not very well defined, right? As to what the answer is. That's also another possibility. But actually, it's not true that a computer cannot do subjective things, right? Like for example, when I log into Netflix, it's actually able to recommend to me what movies I might like. That's a very subjective thing. And more often than not, it's right. How many of you have had the experience that when you log into Netflix or Amazon Prime, it recommends movies that you like? How many of you have had that experience? Right? That's interesting, right? So we just now said that computer cannot do subjective things, but how the hell is it able to do it? Yeah.
Okay, so basically, like in the first one, when we said that it's subjective, it meant that choose that poem to ask it whether it is nice or not. So that was your opinion. Some people may think it's nice, some people may think it's not.
They don't like it, right? But about the Netflix and Amazon, what they're doing is that they see which content you choose to watch and what all you're watching, and then they find like content which is in the same genre, made by the same creator, has the same actors and all, and puts that because they saw that you like this, so they're giving you more. This is based on your preference. The first one, we couldn't tell if it was nice or not because that would depend on a lot of people's preference.
Yeah, so that's an interesting answer. So even though this is a subjective opinion, what we can do is that we can actually analyze data. What we have seen, what other people have seen, and maybe we can do some strange math, stats, and then, in some say, other people who are like you maybe like those movies and maybe you would like them too, and maybe that works, right? So that's actually quite interesting. Similarly, actually, if you log into a shopping site, you do get, you can buy shoes like this, and I did buy. That's very strange that I have shoes exactly that look like this, right? And so that's interesting as well, as to the notion of actually what intelligence actually is. And going to what intelligence is, how many of you have heard about this thing called the Turing test, right? The Enigma movie had it, actually, right? So many of you have heard about it. That's good. So, let me just say what this test is. So Alan Turing, I think, is one of the biggest thinkers of our times in computing. And among many things, including cryptography and so on, he actually was one of the pioneers of artificial intelligence, and he was confronting this question as to how do we know that a computer has become intelligent? Right? Suppose I say, Sriram, I build a computer and say, oh, this computer is intelligent. What is the test that you can apply for that? That test is called the Turing test. And the Turing test is like this, right? You have this room, and there's a human that is interacting through maybe a terminal, and the other side of the partition, there is either a computer or a human. We don't know which, right? Maybe they will toss a coin and they will connect you to either a computer or to a human, right? And you are the tester here, right? And some sessions, right? Maybe 5 minutes you will talk with the computer, and 5 minutes you will talk to the human. You don't know when you are talking to the computer and when you are talking to the human. And the computer is set to pass the Turing test. If this human here is not able to distinguish whether they are talking to a human or to a computer. If that happens, then this computer is now passed the Turing test. I'm sorry. so that computer is set to have passed the Turing test. Right? Do you get it? Right? That's a very interesting way to sort of think about. I don't quite know whether I've actually put the batteries in here. Does it make sense? Right? Because actually, if a computer passes the Turing test, then as far as the observer is concerned, they can't really distinguish whether they are talking to a human or a computer, which means that maybe a computer is able to mimic a human, right? So then it is said to have passed the Turing test. So then maybe a question is actually, have computers actually passed the Turing test right now, right? So this program, it was actually in the late 60s. It is a program called ELIZA. That was actually written by some people at MIT, right? You may have heard about it. That was actually one of the attempts to pass the Turing test. But this attempt failed. Because, by the way, you can actually access ELIZA on the web even today. You could go access it. And if you access it, you will find that, it's kind of repetitive. After talking to you a few times, it's a little bit boring. Right? So ELIZA, even though it was aspiring to pass the Turing test, it didn't really pass the Turing test. Right? How many of you know this movie? What movie is this? Yeah. Yeah. What is the plot in the movie?
I have a vague memory. I think it's about a female robot who these two guys are trying to compute and making it as human as possible.
Yeah.
And the guy eventually falls in love with the computer.
Yes.
Yeah, I think.
Yeah, something like that. Yeah, that's good. It reminds you of some other movie? Okay. So there are many movies like that, right? There are many movies like that. But again, actually, the whole point of that is actually whether that female humanoid robot, whether it passes the Turing test. That was the whole point, right? How many of you remember? I think you're probably too young to remember this, right? How many of you remember the match between Kasparov? So you have a question? Yeah. Okay. So let's go on, and I'll ask you more questions, right? So how many of you remember this match, this chess match between Garry Kasparov and a computer called Deep Blue? What do you remember about it? Yeah, so this was, by the way, a very historic moment when Deep Blue actually beat Kasparov. Up until then, actually, people didn't believe that a computer can beat a human in chess, and Deep Blue was the first one. Today, right? Today, a computer can routinely beat a human in chess. That's how much they've become. This one is actually a different game. It's Go. This is the world champion Lee Sedol, and he lost to a computer as well. The computer is called AlphaGo, and it beat. And then you can sort of see. Here's a person driving a self-driving car, and the car is driving itself, right? So you might now think that, all of these look like, they are passing the Turing test, right? Because we thought that, a computer cannot play chess, it cannot play Go, it cannot drive a car, and now it is passing the Turing test in some sense under these circumstances. And why is this happening, right? Why is a computer able to do all these things? So we will get into what powers these kinds of intelligent, quote-unquote intelligent machines, and what is the math behind them. So we will actually dive into that a little bit, right? The math actually starts with something really, really simple. How many of you have actually learned regression? There's a few people here. Maybe we go to that boy here. Explain what regression is to me. Yeah, maybe give him the mic, yeah.
So basically what I know is linear regression. So it's basically the line of best fit that we have learned in school. And basically that minimizes the mean squared error.
Minimizes the mean square error, right? Yeah, so that's, yeah, that's a rather good description. Now here's a problem that I've picked where on the x-axis I have, I want to calculate, predict a person's income as a function of their years of post-secondary education. Right? It's believable that the more a person studies after school, the more money they might make. Right? That seems like somewhat reasonable. Maybe there are exceptions to that. I'm sure YouTubers don't follow, don't conform to this, but maybe there are exceptions, right? But by and large, actually, this may be true. Similarly, right, another example could be: can you predict a person's height from their age and maybe their ethnicity or something like that? It's probably possible to do that as well, right? So, I think initially we said actually a computer is something that executes a sequence of instructions. So in order for me to actually take the years of post-secondary education and convert it into income, I have to come up with a formula that can take the secondary education as input and crunch something and then say, oh, this person will make 50,000 rupees per month. How do I calculate this formula? Right? So I have to do that, right? How do I calculate this formula? It turns out that you can calculate the formula using statistics. Where you do is you don't calculate the formula. You don't write like, in order to translate Fahrenheit to Celsius, right, there is some formula. I don't remember the formula. It's like 5/2 into something plus something. You can actually do that, right? But in order to convert the years of post-secondary education to salary, what you do is that you don't write a formula. What you do is that you collect lots and lots of data. You collect Sriram has studied this many years after PhD. This is how much money he makes, right? The same for Ambika, same for everybody, right? And then what you do is actually you collect all of the data. Right? And then you have a computer analyze the data using regression, right? And what does regression do? Maybe if I can use that, right? So you have all this training data. You just say X1 is the input, Y1 is the output, right? X1 is the number of years of post-secondary education, Y1 is the income that does this. So this is actually Sriram may study 10 years and maybe he makes a certain amount of money. Similarly, I can do X2, Y2, like that I have lots and lots of data, Xn, Yn. Right? This is data that I've collected. Then from this, what I want to do is that I want to fit a function. Something like y equals ax plus b. Right? Where these are vectors. Y is this vector, x is another vector, and a is a matrix and b is another vector. Right? You have to calculate a and b such that it fits this data. And that's what regression is. The point of least squares is to help you calculate an A and B so as to minimize the error between the actual value and the predicted value by this formula. Right? Do you understand? Okay, go ahead. Yeah.
I have a doubt. Is this formula similar to the slope-intercept formula? Y is equal to mx plus c?
Yeah, so this is a linear equation. This is a linear equation, so it's similar to slope and intercept. Oh. That's what it is, right? So, but in some sense, right, what you are trying to calculate is the slope and the intercept, right? Typically, when you have a line, you are given the slope of the intercept, but here you are given only it's like you are given all these points in the plane, and using the points you have to calculate a slope and an intercept. That is all the point of regression is to calculate that, to sort of minimize the error, minimize the square error, right? That's what regression does. Right? So you know how to do this. They probably taught you how to do this. I can also give you a tutorial, but I'm not going to do that right now. But it's well known how to actually, suppose I give you some data, how do you calculate A and B? It turns out there are many ways to do it. The one way to do it is actually using calculus. What you could do is actually you could actually guess an initial value of A and B, and then calculate what the error is using that A and B, and then calculate the derivative and actually approximate the A and B, using Newton-Raphson method or whatever. There are many methods to do it, right? Using calculus, you can actually start with an initial value of A and B and keep updating that, right? That's actually what machine learning people do today, right? And so this is in one-dimensional space. Here's actually a similar problem in two-dimensional space, right? What I want to do now is, given the size of a house and the number of bedrooms, I want to calculate, what the price of the house is. Those two are inputs. The inputs are size of the house, maybe in Delhi, and the number of bedrooms the house has. Using those two, can you estimate the price of the house? Again, the easiest way to do that is to collect lots and lots of data. Collect, 3-bedroom houses with 2,000 square feet, and then do all of that and plot that data, and then fit a plane in order to answer that question. So you can now imagine this can be done, right? Because you can do that by this, right? Now these are linear relationships, right? So you said actually this is a straight line. So these things linearly relate the inputs to the outputs. The world is far more complicated. Not everything in the world is a linear relationship. There are many non-linear relationships. In many cases, the relationship between the output and the input and the output are very, very complicated, right? So then you have to think about, you have to now think about, quadratic features. Maybe you have to think about x square. Maybe I have two inputs, x1 and xy. I need to think about x1 times x2, right? The math becomes complicated, right? It turns out that there are these things called neural networks, right? These are nothing but regression on steroids. That is all these are. So what actually happens is that now you take these inputs and then you pass them through these things called neurons. What these neurons have is actually in every one of these neurons there is a non-linearity. There is a non-linearity in the neuron, and then there is actually a linear function. That's what those are. It's a composition of both those things. And you could think about this, each of them is doing some curve fitting. Each of them is actually trying to figure out a slope and a y-intercept. That's how you should think about it, right? But you connect them all in a network, and it turns out that these kinds of networks are able to model very non-linear relationships. Even if inputs and outputs are non-linearly related, right? These networks are able to represent those non-linear relationships, right? That's a very miraculous thing. It's very surprising if you sort of think about it, right? And what can you do with these things? What you can do with these things is that you can actually do things like this, where you can now build a neural network that can differentiate pictures of cats and dogs. Suppose I ask you, right, my goal is now to build a computer which, as an input, I give a picture. The picture could be a cat picture or a dog picture. And the goal of the neural network is to determine whether the picture is a cat or a dog. That's the goal, right? Now, I think you first said actually, what a computer can do is actually to write it can execute a sequence of instructions. Can you think about a program that takes a picture, analyzes the picture and tells you whether it can, what algorithm will you use? Computer vision. Yeah, you could use computer vision, but I can imagine an algorithm to sort numbers or arrange them in ascending order. You have to tell me an algorithm to just look at a picture and tell me whether it's a cat picture or a dog picture. How will I do that? Yeah, how would you?
So I think what I do is I will myself, if I have to be purely coding based, so I will myself first see characteristics of cats which are similar throughout, and some characteristics which are in some subsets, and then ask the computer to check for those characteristics. Same with dogs. So for example, if I have a mouth of a specific shape, I'll tell the computer to recognize it as a cat or a dog based on that.
Yeah, so this is, by the way, this is very interesting.
Supervised learning mechanism is what you're saying.
Yeah, exactly.
So the deal is the following, right? It turns out that these kinds of approaches, people tried for a very long time. They never worked. Because the cat might be facing away from you. It might be, it might be blurred, it might be on the other side. All kinds of things can happen, right? So it is very difficult, give me a second, it is very difficult to write a program with a sequence of rules that determines whether something is a cat. Because it's a very difficult problem to do. People have tried. It's not like people have not tried. They've tried for a long time. But what has worked is that you collect thousands and thousands of cat and dog pictures. People have nothing else to do other than post them on Facebook and Instagram anyway. So there's enough pictures available, right? It's not like, it's not, I don't even have to put effort to do that, right? So I collect all of them, but I have to label. Yeah, go ahead. What's your question? Yeah.
Sorry, it's not really a question. A convolutional neural network can be used. Basically, as you said, there can be a data set of many images of cats and dogs together, and then what basically the neural network does, it reiterates over the different images that there are. And for example, if there's a 10 cat images, or 10 cat and dog images, the cat images that it gets, it then filters it out, then it filters out again until it reaches upon a point where it can identify that it's a cat image or not.
Yeah, that's interesting. Yeah, so you know, I'm going to not take questions on that, but I think what he described is actually very accurate, right? So I'm going to just demystify that a little bit more. So what you can do is that, you know, you can collect a lot of the images and you have to label them. You have to label them saying actually these pictures are cats, these pictures are dogs. And then you have to fit a quote-unquote regression model. Actually, this is actually called a classification problem. Because in a regression problem, you have, you know, a numerical output. In a classification problem, you have a binary output. You either a 0 or a 1, cat or a dog, right? And you can compute, you know, these kinds of slopes and y-intercepts for every one of these neurons, right? Such that you maximize the chances of the cat being classified as a cat and the dog being classified as a dog among your training data. This is called training data. And if you pick the neural network well, and you pick the training data to be sufficiently exhaustive, then this neural networks generalize, which means that I can actually give a new cat picture or a new dog picture that I have not seen before, and it's actually able to predict accurately whether it's a cat or a dog, which is why this system actually works, right? But note this, right? Even here, what I have to do is that I have to first collect a lot of training data. Because I have to first collect a bunch of cats and dog pictures, I have to label them, then the process of calculating this, doing this regression and calculating these A's and B's, right? That is called training, right? So you basically teach a computer saying these are cats, these are dogs, and from that, using that, right, you calculate the weights of each of these neurons. That's called training. And once the training is done, you can give new pictures, cats or dogs, and then it will tell you whether, that's called inference, right? But again, note that actually in order to do that, right, I have to do a lot of calculation. This is actually supervised learning. This is supervised learning. That's actually interesting, right? So we will talk about unsupervised also a little bit next now, right? So the difference between supervised and unsupervised learning is that, go right ahead, yeah.
Deep learning or machine learning for it?
Can you use?
Deep learning or machine learning to get the outcome.
Oh, to do the labeling itself. Yeah, that's an interesting question, and that's what we're going to do next, right? So the difficulties with these things are manifold, right? It turns out that for every problem, we need to generate this kind of label training data, right? So you might actually build a neural network that classifies, you know, cats and dogs, but can it also identify panda bears? You have to now retrain it, you know, with panda bears, right? Suppose I build a neural network to classify cats and dogs, right? Can that neural network translate Hindi sentences to Tamil? No, but I trained the neural network to classify cats and dogs. Can that neural network? No, it can't do, right? So in order to now it's not trained for that, right? So in order to translate Hindi sentences to Tamil, what I have to do is that I have to calculate I have to create training data which contains parallel corpus of Hindi and Tamil sentences, right? And then I have to train a neural network for that purpose. And that will now translate Hindi to English. So for every problem, I have to now create training data. I have to train a different neural network. That also seems very, very difficult to do. And these things are inflexible. So even though they are quote unquote intelligent, they are very task specific. Okay, I'll ask this girl. Yeah, what do you want to know? Yeah.
Sorry. So I have learned that before a neural system, like we use functions like sigmoid or stuff. So like, aren't we using it over here to like produce outcomes as 0 or 1?
Okay. Yeah, so absolutely. I mean, these non-linearities are very, very important. That's what gives us the ability to recognize these things. Yeah, go ahead.
So how does the classification model really work?
How does it really work?
What is the underlying mechanism?
So the underlying mechanism is like very much like, you know, this really simple problem we discussed where, you know, you go from, years of post-secondary education to salary, right? We actually saw that as a graph, and the goal was to calculate an A and B that fits the data, right? It's the same thing that's going on here. That's all that's going on. They said that the data is much more complicated. It's higher dimensional, right? And there are many, many parameters like A's and B that you have to infer for all of these neurons. You may have to, you know, infer hundreds of thousands of parameters, but the same math. And there is some, there's some more complicated, thing. There's something called back propagation that you use to train these things. That's all detail, right? But you just fit some parameters to fit the data. You learn some parameters to fit the data. That's all you do, right? But the problem is that for every problem, you need a different neural network. And for every problem, you need to create labeled data, and then you create a neural network just to solve that problem. Right? That's very tedious to do. But the whole ChatGPT revolution started because 3 things happened. This was real disruption. The first thing that happened is actually there's something called a transformer architecture. This was actually a paper in 2017 by people from Google. The paper is titled "Attention is All You Need," and this came up with a neural network architecture. It turned out that this neural network architecture suddenly started working for all problems. See, before this, right, people had one kind of architecture for maybe recognizing images, another kind of architecture for natural language processing, for trying to translate between one language to another. Suddenly, right, this architecture suddenly started working for every problem. The second thing that happened was, but again, right, even though this architecture worked for every problem you had to create your own training data. You had to create training data to distinguish cats and dogs. You had to create training data to distinguish, translate Hindi to English. That problem was still there, right? There's another really surprising thing that happened called self-supervised learning. So the girl here was talking about unsupervised learning, right? So let me actually say a little bit about what self-supervised learning is. What you do in self-supervised learning is that you just look at data that is present in the internet. So how many of you recognize this passage? What is this passage from? What is this passage from? So whose speech is that? This is Jawaharlal Nehru's speech, right? Very famous speech. So, and we could find many such speeches in the internet, many documents. And what we are going to do is that we are going to take this speech, this document, and we are going to play hide and seek, right? Let me say what the hide and seek is. I'm going to hide this one word here in the input, right? And then I'm going to give this input with this one word hidden to the neural network. And I'm going to now say the output is the hidden word, because I know what the hidden word is. But I'm going to ask the neural network to calculate trist as an output with this as the input, right? Then what I'm going to do, I'm going to hide another word, right? But I know what the word I've hid is, right? So I'm going to ask this neural network to calculate destiny as the output when I give this as the input, right? I'm going to now do this for every interesting word in this paragraph. And I'm going to do this for every paragraph in Nehru's speech. And I'm going to do this for every speech that has been ever given, ever, that's available on the internet, right? I'm going to do this for every document that I can find on the internet. So I'm going to now play this massive hide and seek game, where I have now built what is called the universal fill-in-the-blanks provider. Like, basically I can actually now take any document, create a blank. And this neural network is capable of filling in that blank, because it has been trained with all of the world's data. Right? And in order to do that, right, I don't need any supervision. I don't need anybody to label anything. Right? Because I'm playing the hide and seek game, because I'm actually blocking something and I'm actually asking the computer to guess that. Do you understand that? So this doesn't require any supervision. It doesn't require a human to actually say that these are cats, these are dogs, because I'm hiding them myself, and I'm actually using the neural network to just discover what I've hidden. That process can be automated entirely. Is that clear? Right? So that's actually called self-supervision. So that was the second disruption. The third one that people didn't anticipate was that, okay, so now I can use this. Oh my God, yeah. So I think I missed something here. The third thing is scale. It so turned out that if you now take all of the world's data and play this hide and seek game, by the way, you can actually do that not only for text, but you can also do that for images. I can actually hide a portion of the image and actually ask the neural network to guess what portion I've hidden, right? And you build larger and larger neural networks with more and more data. right? And that's what actually this community has done. I mean, starting with, there was a neural network called Elmo that was built in 2019 with 94 million parameters. And if you look at actually how these large neural networks have progressed, right? With BERT and GPT-2 and GPT-3 and now GPT-4, the number of parameters have gone up by a factor of 10 every year, right? We started with 94 million parameters. Now we have hundreds of billions of parameters. These are bigger and bigger neural networks, right? And one of the amazing things that happened when people started doing this kind of self-supervision on big neural networks is that they started having something called emergence, right? And this is something that we don't understand very well, right? What happened was that as the number of parameters increased, even though these neural networks were trained to fill only the blanks, they started doing other things that we didn't train them for, right? Even though we trained them only to fill in the blanks, at 8 billion parameters, they started answering questions, right? You could actually train the same fill in the blanks neural network with 8 billion parameters and you can ask some question, oh, what happens here, right? And it was able to answer those questions based on the data that it was trained on. At 62 billion parameters, right, this neural network started summarizing. You had the ability, these neural networks now have the ability to summarize a big paragraph and then give you a summary, even though we never trained for it, right? At 540 billion parameters, right, these things started completing code. You could write actually, 10 lines of Python and these things would complete the remaining lines that you didn't complete, right? This phenomena is called emergence, right? And here's a very nice picture. This is by my colleague Sebastian Bubeck in Microsoft Research in Redmond. He tried this, this is actually a text to image conversion application. You're supposed to be given a text and the model's job is to give you a picture consistent with that text, right? And the text he gave is a portrait of a kangaroo wearing an orange hoodie and blue sunglasses, standing on grass in front of the Sydney Opera House, holding a sign on the chest that says, "Welcome, friends," right? And as you increase the number of parameters from 350 to 750 million to 3 billion to 20 billion, you can sort of see how much better the picture gets, right? And this actually is something amazing that has happened, right? So the combination of this transformer architecture, the self-supervision, and just more and more parameters is causing, these neural networks, which were originally trained only to fill in the blanks, they are now having emergent capabilities and they are doing things that we didn't train them for, right? So I hope I have communicated the surprise there to you. We never really trained them to do these things, but they are able to answer things that we never trained them for, right? So now this actually now answers the other problem. We don't have to build separate neural networks to solve different problems. These networks are now able to become general question answering systems for any kind of question. They have actually gone through all the text that is present in the internet, all the images present in the internet, all the videos present in the internet, and in some sense they have understood something about them. And they are able to engage with you about that content the same way anybody else would. Yeah, go ahead. Yeah.
So, can you tell me how many billion number of parameters did AI actually start hallucinating, like we know ChatGPT and all? So, at how many parameters did it actually start it, or approximate number?
Oh, okay. So we will cover hallucination. I mean, even small neural networks, big ones, they all hallucinate. Right? We will actually talk about hallucination a little bit later. Yeah, it depends on a variety of things, right? But one of the problems that these large language models have is actually they do hallucinate. So we'll talk about that a little bit more. Yeah. Okay. So so what is intelligence? So we started with the Turing test. So a computer can now, in some sense, right, mimic what humans can do in many ways because they actually are able to read and process large-scale data, and in some sense they can replay patterns from the training data in mysterious ways, right? Somehow they're tapping into the collective intelligence of all of us, and they're able to sort of, in some sense they have like read all the books, all the internet, they've watched all the movies, right? And then they are able to sort of, when you ask a question, it is able to bring the right patterns from all of the data that it has seen, and it is able to give you an answer, right? I mean, that's actually the reason why, this revolution is happening. But this is actually leading to very many interesting applications, right? Let me show you a few. So this one is actually the GitHub Copilot. This was the one that I actually first was stunned by because I'm a programmer. And, I first saw actually, as the experience, how many of you have used GitHub Copilot? right? Some of you, but if any of you do programming, right, you would probably use this assistant. Many platforms now have that. The experience is that you could actually type code and the thing completes it for you, right? As you type, it sometimes completes a sentence. It sometimes completes the entire function, right? And I'm a programmer, and actually I was stunned by how much better it was getting every month, right? That's how I got interested in this problem. Is actually, it's remarkable how good it is, right? So here's another interesting application. This is actually something I tried, after GPT-4 Omni was released. I took this picture, in my kitchen table, and I asked it actually, give me a good dessert recipe I can make with these ingredients. And the system was able to recognize that I had 4 or 5 lychees, a mango, a banana, and an apple, and it asked me to go buy Greek yogurt and honey, and then it gave me a recipe, right? But I was like stunned by how it was able to understand this picture and what this picture actually has, even, right? So these things actually have become multimodal. They are no longer just taking words. You can take pictures, you can actually give images, you can actually give audio, video, and so on. It's stunning. Let me show you next actually a application that colleagues of mine at Microsoft Research India have built to help teachers organize lesson plans in government schools in India. Let me show you this application.
Sikshana Foundation started as an NGO that's focused on the education sector. We are working in 6 states across India in about 50,000 schools, impacting nearly 3 million students.
The public school system in India has been severely stressed. We found that typically a teacher handles multi-grade, multi-subjects, especially in the rural areas of the country. The biggest challenge was creating lesson plans.
Preparing those lesson plans, it was taking a lot of time because everything was manual. We were writing and writing and writing.
And that's where I felt technology can help.
Shiksha Copilot is a generative AI solution where we want to empower teachers to create engaging content for their classroom. These teachers are able to generate lesson plans. They're taking the activities that are generated and they're using all of this content in the classroom.
Within 5 minutes or 2 to 3 minutes, I'm preparing the lesson plans.
It's very essential that any solution we roll out supports the local language.
ಟೀಚರ್ಗೇನು ಫ್ರೀಡಮ್ ಇರಲಿಲ್ಲ, ಅದು ಹೇಗಿತ್ತು ನಾವು ಹಾಗೆ ಉಪಯೋಗಿಸ್ಬೇಕಾಯ್ತು. ಆದರೆ ಈಗಿನ ಲೆಸನ್ ಪ್ಲಾನ್ನ ನಮ್ಮ ನೀಡಿಗೆ ತಕ್ಕಂತೆ ನಾವು ಕ್ರಿಯೇಟ್ ಮಾಡ್ಕೊಳ್ಳಿಕ್ಕೆ ಟೀಚರ್ಗೆ ಫ್ರೀಡಮ್ ಇದೆ.
Shiksha Copilot is based on Azure OpenAI. It's grounded in local context.
ಈ ಮಾಮೂಲಿ ನಾವು ಕ್ಲಾಸಲ್ಲಿ ಪ್ರಯೋಗ ಮಾಡೋದಕ್ಕೂ ಶಿಕ್ಷಾ ಕೋಪೈಲಟ್ ಲೆಸನ್ ಪ್ಲಾನಲ್ಲಿ ಕ್ರಿಯೇಟ್ ಆದಂಥ ಹೊಸ ಪ್ರಯೋಗಗಳನ್ನ ಮಾಡಿದಾಗ ಅವ್ರು ತುಂಬ ಒಂದು ಖುಷಿ ಪಡ್ತಾರೆ.
The problems that are faced are pretty much universal. So if we have a solution that works in just one state in India, we think that solution can go global.
To me, when I see that video and when I had a chance this morning to meet them, the thing that sort of really inspires me is that combination of folks coming together, right? Which is Microsoft Research India, a non-profit organization, and the teachers all co-designing it together. I mean, when you have that type of feedback loop creating new products, that's magic. And that, I think, is at the end of the day what we all live for, and it's fantastic to see that.
Yeah. So I want to show you one more, actually. I think I found very interesting. Let me actually just switch this over. I have, I don't know how many of you have seen this. This I found very interesting as well.
My name is Anton and I'm from Ukraine. As a freelance developer living with cerebral palsy, tasks like typing and speaking can be difficult, which limits my ability to communicate effectively. My first laptop only had DOS and there were no accessibility features available. To type a parenthesis, I had to press Shift+9, but I could only use one finger, so I had to hold Shift with my nose. If you try working like that, you'll quickly understand why I couldn't afford to fix my code many times. I realized early on that I was different from others and encountered discrimination and inequality at a young age. At that time, I was torn between stereotypes about disabled individuals and my own abilities. And I managed to learn that language in 1 month. So I started to learn more and more programming languages. I was about 14 when I created my first program. Later on, it became easier for me to write code as I learned about autocomplete. I learned Git and started using private repositories. I always inform my clients about my disability. Moreover, I present it as an advantage because it provides me with extensive experience in solving complex and unconventional problems. When I first heard about GitHub Copilot, I was doubtful that it could handle such a complex task as coding. But I was surprised at how helpful and relevant the suggestions it gave me were. Sometimes, it even seemed like it could read my mind because it would suggest code that I hadn't thought of yet. Although this particular aspect of AI may not be widely discussed, it possesses the power to counter my pessimism by presenting optimistic alternatives, helping me overcome mental challenges. I can now not only write the code itself but also detailed comments, documentation, and project descriptions. Previously, I physically couldn't afford to do this. I firmly believe that AI has enormous potential to make a positive impact on the lives of people with disabilities. Through my active engagement in studying machine learning and conducting research, I aim to harness the power of AI for the betterment of our lives.
Yeah, so that was actually very interesting, right? And let me get back to my slides now. Yeah, so that is actually quite interesting, right? Because in some sense, right, what we really have is we started with sort of building a general purpose fill in the blanks calculator, but it's able to do many things. It's able to complete code. It is actually able to, what you saw in the Shiksha Copilot is that if you give it sort of the whole curriculum and a bunch of videos, and then we can actually create, we can ask the AI to create a lesson plan for maybe 8th grade algebra and Kannada. It can actually do that. So these are very, very interesting things, right?